Alright, so in this lesson we're going to be talking about acceleration, which I just view as being kind of the third step up on the motion topics we've been talking about. The first one being position. Uh, when you change in position, the rate of that change is called velocity. And then, obviously, most things we encounter do not travel with a constant velocity, so that change in velocity is then what we refer to as acceleration. So if you're driving your car, the velocity, the instantaneous velocity anyway, would be the number you see on your speedometer. The acceleration would be how quickly the speedometer moves. So just take a minute and think what you already know about acceleration. I want you to compare these two motion diagrams, and we've already discussed how different spacings in the time intervals mean a changing velocity. But let's just draw vectors on these. So since the top motion diagram has equidistant spaces, all of our velocity vectors are going to be constant throughout. This is uniform motion with a constant velocity. When the spacing becomes larger over every time interval, that's when we know we have acceleration. So in other words, over time, my velocity vector gets bigger and bigger. That's not the only way acceleration can occur though, because acceleration is any change in velocity. So let's just make a velocity versus time graph. As an example here. So let's say we have 1, 2, 3, 4, 5. This is our velocity in meters per second. And this is our time in seconds. So we got 1, 2, 3, 4, 5. So if I start off at rest at 0 seconds, I'll have a dot here. Then let's say after 1 second my velocity reaches 2 meters per second. Then after 2 seconds I'm at 4 meters per second. And at 3 seconds I'm at 6. So on and so forth. And I'll have a line, which means I have a constant acceleration. The reason I know I have a constant acceleration is because my velocity is increasing over time. Now, in order to find that, just like we found velocity on a position versus time graph, we can find acceleration on a velocity versus time graph by looking at the slope. The slope is again our rise over run, which is 2 over 1. In other words, 2 meters per second over 1 second. Since I'm dividing by seconds twice, it's also going to be 2 meters per second, or 2 meters per second squared, which is the SI unit for acceleration, whichever way you prefer to notate that. Both of these are technically correct, but you'll usually see it the shorthand way, 2 meters per second squared. So the definition of acceleration, it's the rate at which an object's velocity changes. Now there's three different ways the acceleration of an object can change. The object can be speeding up and its velocity is changing. It can be slowing down and its velocity is changing, or it can be switching directions. Remember, velocity includes speed and direction, so a change in direction also indicates a change in velocity or an acceleration. So like we said, the average acceleration is if I'm taking it over a time interval. So if we go back to this slide, I'm taking the acceleration over this 2-second time interval, so therefore it is an average acceleration. On the other hand, if I wanted to find the instantaneous acceleration, I would be concerned with the tangent line of the curve. So for instance, let's look at this example. When I have a linear acceleration, any point, because this is uniform acceleration, any point the line tangent is going to be the line itself. So at any point on a linear graph, the acceleration stays the same, which means constant acceleration. And just keep in mind, this is a velocity versus time graph. Let's look at another velocity and time graph. What if your acceleration isn't constant? What if you are speeding up for a while and then you're not speeding up as much for a while, and your acceleration line might look something like that? And I want to know the acceleration at this point, the instantaneous acceleration at that point. Well, a tangent line, remember, is a line that only touches the graph at that particular point. So the tangent line would look something like this. Now I can calculate the rise over the run of this line, and I can obtain the instantaneous acceleration. We're only really going to deal with constant acceleration in a lot of our problems, but just keep in mind that you can find the instantaneous acceleration by taking that tangent line to the curve, the slope of that line. You can also use vectors to represent acceleration. With our motion diagram, if you remember, we drew those vectors representing the velocity at each point. When we look at it as something changing speed, getting further and further apart, our velocities might look something like this, where they keep increasing in size, increasing in size, increasing in size. If each of these time intervals is 1 second, then what we can do is take our first velocity. We'll look at, we want to find the change in velocity. So what we want to do is take our final velocity we're looking at minus our initial velocity we're looking at. In this case, 5 was our final, 1 was our initial. So we can take 5 minus 1, which is going to look something like this, and our change in velocity looks something like that, which over that 4-second time interval would be divided to get our average acceleration. If we wanted to get our average acceleration over the time interval of 1 second, for instance, this one, like I said, would be divided into 4 because we looked at 4 seconds. If we wanted to, let's just look over 1 second. We have 2 minus 1 So our acceleration is something like that. I know I'm just drawing, these aren't to scale, but basically the acceleration equals the uh, final velocity vector minus the initial velocity vector divided by the time interval you're looking for. So that in this case my time interval was 1 second. In the first interval, the first example, my time interval was 5 minus 1, which was 4 seconds. That's why I divided it into 4. I know I wasn't quite clear about that, but hopefully you realize why I had to divide that, because it was over a 4-second time interval. Now let's look at this example. How would you describe the sprinter's velocity and acceleration? Well, we can see that the velocity is not constant because it's increasing, it's increasing, it's increasing, and it starts to stay constant, almost. If we want to find the instantaneous acceleration, what we want to do is, because we know the acceleration is not constant, for the acceleration to be constant, the tangent line would have to be consistent on all points of the graph. But this, as you can see, when you draw a tangent line at 1 second and a tangent line at 5 seconds, you get two totally different lines with totally different slopes, which means that your acceleration is not constant in this case. You do not have constant acceleration. So we can get our instantaneous or average accelerations if we want to. By finding the slope of those two tangent lines. Now let's look at this example. Let's try to describe what's going on in this graph. Let's say it's a dog. First of all, the dog at 0 seconds has some velocity. So the dog is moving, it's changing position for 2 seconds. It's not accelerating, therefore it has a horizontal line with 0 slope, so its acceleration is 0. Now the dog's velocity decreases to this point over the course of 2 to 3 seconds. So 1 second, it's got a velocity lower than it had, so it's got an acceleration, it's decelerating. And then again, it has another point in time where its acceleration is 0 because we have this horizontal slope. That doesn't mean the dog is still, it just means the dog is moving at a constant velocity. Now the dog continues to decelerate where we have this negative slope here. So we have some acceleration here, we have some acceleration here, but again a horizontal slope indicates 0 acceleration. So now the dog actually is not moving because the dog has 0 velocity. So it's got 0 acceleration and 0 velocity. Finally, the dog picks back up speed very quickly, very high slope, so very high acceleration here. We had deceleration here, and then again we have 0 acceleration, but the dog is moving because if you look, it does have a value for velocity. So hopefully you get in the habit of reading these graphs, knowing that positive slope means positive acceleration, negative slope means negative acceleration, 0 slope means no acceleration, constant velocity. I just want to look at one more. See if you can find the train's average acceleration between 0 and 5 seconds, and then between 15 and 20 seconds. if you haven't already paused the video to try this, do that now because I'm going to go over the solution here. Between 0 and 5 seconds, we're looking at this time interval here. Our velocity, we want to do the change in velocity over the change in time, which is going to be 10 minus 0 over 5 minus 0, which is 2 meters per second squared. If we're looking between 15 and 20 seconds, as the other one asks, we have our change of 10 to 4 over 20 minus 15, which is 6 over 5, or 1.20 meters per second squared. So let's just talk about positive and negative acceleration here. I mentioned those a little bit in the earlier graph. When you have a positive acceleration, you have a positive slope. Negative acceleration is a negative slope. 0 is a horizontal slope. We could have a positive velocity a negative velocity. Say our origin here, a positive velocity would mean I'm moving away from the origin. A negative velocity would mean my position is changing towards the origin in a negative direction. We could also have the case where I'm speeding up and I'm slowing down. Now, when I'm speeding up with positive velocity, my velocity is getting bigger over time, and I'm moving away from the origin. So I'm going to have a positive acceleration. When I have a negative velocity, when I'm moving toward the origin or away from the origin in a negative direction, and I'm speeding up, I'm also going to have a positive acceleration, because my graph of that would look something like this. I would have my velocity would be decreasing, and it would be negative. So since my velocity is negative, it's going to be below 0. And if it is actually speeding up, my negative values would be getting more and more negative. So it'd have something like this. Or I'm sorry, I made a mistake here. I apologize for that last video. I want to redo this explanation real quick. So there's 4 scenarios. We could have a positive velocity, meaning I'm moving away from the origin or to the right and negative velocity mean I'm moving to the left. And we could also have a positive acceleration, meaning I have a positive slope, and a negative acceleration, meaning I have a negative slope. So let me just draw all four of these scenarios. This one, these are all velocity versus time graphs. The first one, I have a positive velocity and a positive acceleration. In the second one, I have a positive velocity and a negative acceleration. In the third one, I have a negative velocity and a positive acceleration. In the fourth one, I have a negative velocity and a negative acceleration. So in my signs for velocity, notice that in this example and in this example, the speed is increasing. The magnitude of my velocity is increasing. Because this example, it's getting more positive. In this example, it's getting more negative, but the number itself is getting bigger. So when I have the signs of my speed or my velocity and my acceleration consistent, meaning they're the same, then that tells me I'm speeding up. For the other two examples, since the signs of velocity and acceleration are opposite, that means that they are slowing down. That's just a general rule you can remember. If an object has the same sign for velocity and acceleration, that indicates it's speeding up. I'm sorry about the confusion in the last video there. I got a little tied up there for whatever reason. But let's just look at these examples here. Tell me whether each of these are speeding up or slowing down. First, let's look at A. What do you think A is doing? If you said A is doing neither, you are correct, because A has a horizontal line, meaning it has zero slope, zero acceleration. B. B has a positive slope, and meaning it has a positive acceleration. It has a positive value of velocity because it's above the zero. So it's speeding up. How about C? C also has a positive value for velocity, but it has a negative slope, meaning it has a negative acceleration. So C is actually slowing down. How about D? D is an interesting case because D starts off with a negative velocity and a positive acceleration. It ends with a positive acceleration and a positive velocity. So it's actually slowing down than speeding up. So what happens here is, for instance, if it's a runner, the runner slows to a stop, turns around, and speeds up. Because the velocity changes from a negative velocity, meaning it's moving to the left, and it ends up in a positive velocity, meaning it's moving to the right. Finally, E, basically the same as A. It's neither, but it has a negative velocity, unlike A, which had a positive velocity. So mathematically, acceleration, the average acceleration is defined as the change in velocity over the change in time. We've already discussed that. Now let's work on the sample problem here, where we've got the motion of a ball. We roll it up a slanted driveway uh, and with a speed of 2.50 meters per second. It then reaches the peak of the driveway after 5 seconds and it starts to roll back down. First of all, describing that, the ball is going to move upward. So it's going to have actually we'll say this is the origin. It's going to have a positive velocity, but it's slowing down. So it would have the opposite sign for acceleration. Until it stops. Then it's going to have a negative velocity and it's speeding up, so the signs are the same. It's actually going to have a negative acceleration. That's a little tricky, but accelerations you can kind of think of as being something where you're being pushed or pulled by something. In this case, gravity is constantly pulling that ball in a negative direction. We'll get into that more when we talk about forces, but the reason the acceleration stays negative is because you've got a constant pull from gravity. It starts moving this way, so it starts with a positive velocity. It ends moving that way, so it ends with a negative velocity. So the sign of the acceleration is always negative. To find the magnitude of the ball's acceleration, what we want to do is always start off looking, well, we want to draw a picture, which we just did. We also want to look at the values we know. We know that the change in time as it rolls up is 5 seconds. We know that the initial speed is 2.5 seconds. Let me just double check the sig figs here. Looks like we've got 5 seconds is our lowest amount of sig figs. So we've got our final velocity, which is, we know it rolls up. Anytime you see rest in a problem, that's going to mean 0 meters per second because it's not moving, it's staying still. So my acceleration is going to equal my final velocity minus my initial velocity. Over my change in time. This is going to be 0 meters per second minus 250 meters per second over 5 seconds. So negative 2.50 meters per second over 5 seconds yields 0.5. Negative 0.5 meters per second squared. Our acceleration is indeed negative and the magnitude is 0.5. Does that seem reasonable? I believe it does. It's not that big for a ball. So why don't you try this one, pause the video, because I'm going to go over it immediately here. But the car's velocity goes from the initial velocity of 4 meters per second to a final velocity of 36 meters per second over a change of time of 4.0 seconds. Now my average acceleration is final velocity minus initial velocity over change in time, which is 36 meters per second minus 4 meters per second over 4 seconds, which is going to come out to 32 meters per second over 4 seconds, which is 8 meters per second squared, 2 sig figs, so we'll say 8.0. And my average acceleration is a positive 8.0 meters per second squared. Let's look at one more. We've got a bus moving at 25 meters per second, starting at 25 meters per second. Comes to a stop over a course of 3 seconds. So my final velocity is 0 meters per second. What's my average acceleration? Same deal. We take 0 minus 25 over 3. We get negative 25 thirds, which, if I do the math correctly, is going to be negative 8 point, I believe 8 1/3, so with 2 sig figs, negative 8.3 meters per second squared. For a bus, a little bit bigger acceleration makes me content there. Not that the size of the object really matters all that much, but these aren't, we're not talking about space shuttles or anything like that. We're just talking about marbles and buses, which shouldn't have huge accelerations. Finally, I'd like you to try these on your own. Go ahead and try to sketch a velocity time graph for a car that goes east at 25 meters per second for 100 seconds, and then west at that speed for another 100 seconds. And then the second problem I'd like you to try on your own. A canoeist paddles upstream at 2 meters per second, turns around, goes downstream for 4 meters per second, at 4 meters per second. Turnaround time takes about 8 seconds. What are the average velocity and average accelerations of the canoe? All right, thank you very much.